Good morning, everybody, and welcome to week 4 of the CWS preparation course. This is for the Level 1 certification, and this is week 4. Today we're going to be talking more about water chemistry, which I know everybody has been looking forward to all week long, ever since we finished last week's class. I bet you guys were going, oh, man, I wish we could have more of that chemistry. That was so much fun. Well, here we are. The wait is over, and so let's get right to it. Those of you that have heard my presentations in the past know that I always start off with thank you, and I mean it very much. I really do appreciate the opportunity to serve you guys in this way, and it's always my goal to make sure that the information that I give to you is at least as valuable as the time that you give to me, and so I definitely appreciate it. Thank you. I just realized I'm missing my duck on this page. This is a first. You guys have witnessed it. No duck on the thank you page. That's got to have the duck. I don't know where the duck went. I have to fix it. Anyway, so today what we're going to talk about, I know that probably doesn't concern you guys nearly as much as it does me, but you know, my duck is, it is the source of my masculinity, of my pride, of my strength. The duck has to be there. I don't know, what is a man without a duck? Anyway, what we're going to talk about today. We're going to talk a little bit about stuff we talked about last week, just review it a little bit, and then a little bit more about, or we're going to talk about some about oxidation and reduction, and ions, which are always fun, pH, acids, bases, and salts, and some other stuff we find in the water. All right, so this is for Jen because she loves this show, Sheldon. Neutron walks into a bar and asks how much for a drink. The bartender replies, for you, no charge. And that's actually, if you remember last week when we talked about protons, electrons, and neutrons, the neutrons carry no charge. They have no electrical charge. They simply add mass. They sit in the center, in the nucleus of an atom, and they do not carry a charge. All right, so remember last week we also talked about the creepy Kool-Aid guy and heterogeneous mixtures and homogeneous mixtures. Okay, so a heterogeneous mixture was sort of like a bowl of mix, trail mix, where you take a sample from one side of it and you test it. It could have different amounts of sunflower seeds and M&Ms and other cashews and raisins and all that stuff on one side. It may have a different amount than if you take a sample from the other side of that bowl. And so that's a heterogeneous mixture. A homogeneous mixture is where everything's the same. It doesn't really matter where you take the sample from. You're going to have pretty much the same chemical makeup anywhere. That's a homogeneous mixture, and Kool-Aid was an example of that. Usually like a bucket of water would be, or a pond or a lake might be as well. Then we talked about the pure substances, how elements form compounds when you put them together, and a compound has 3 characteristics that define it as a compound. Pretty much every compound out there has a definite boiling and freezing point, has well-defined characteristics of their own. They're different from their component elements. That means that, like salt, for example, sodium chloride, the sodium is going to be the silverish metal, and the chloride is going to be a greenish gas. So, and then they're always homogeneous as well. Okay. We talked a little bit about the periodic chart of the elements. Where you can recall anything in the same vertical line carries the same chemical properties as anything else in that same vertical line. So that is why you have magnesium and calcium, for example, are all going to be they're going to be able to be removed by a water softener, by resin, and that's because they're in that same vertical line, right? Also, you have barium is a big one that we run into. It's usually talked about in the owner's manuals in a water softener, that if you have something like barium in the water, then it will reduce the capacity of that system. had to take a sip of my delicious, delicious coffee made with high-quality reverse osmosis water. It was yummy. Hope you guys are drinking coffee, or drinking your coffee or tea, or actually it's a vice, so water. Hope you're just drinking pure water. But, pure is a subjective term. We're going to talk about that later. In code of ethics, there's no such thing as actually pure water except in a laboratory setting. So high quality water would be more appropriate. Also, sodium, potassium, right? They're in the same vertical line. That's why you can regenerate a water conditioner. You can also use anything. Actually, in fact, hydrogen is commonly used to regenerate a water softener, or at least a deionization system, at least on half the DI system, because that's the side that takes out the cations. You would use oxygen or some form of an oxygen to remove the anion side. Okay, so this periodic chart of the elements. Atom, an atom is the smallest possible unit of an element. A molecule is two or more atoms of one or more elements put together. So here we see just the single guys right here, right? And then you take two of those, that becomes a molecule. And then you start adding a bunch of different stuff together. You've got molecules of a compound. And then a mixture is when you take a bunch of those compounds and atoms and you throw those all together. That's a mixture. The anatomy of an atom, if you recall, we have the nucleus here, which is, go back, sorry. The finger happy here. You have the nucleus. That's where the proton and the neutrons exist. And then the electrons, they're the planets. Remember, okay, so the nucleus is like the sun in the center. That's where the protons, positive proton, in case you're wondering, you know, positive. It all has the P sound there. And I just felt like I was on a Sesame Street episode for some reason. Proton. Anyway, count them. One, electron. Anyway, actually it's the neutron simply adds weight, and it exists in the nucleus. It exists in the nucleus, the neutrons do. Thank you, Jim. You may see that somewhere again. So you know what happens when you get your certification? You can just basically forget everything. That's the cool thing about the certification. You don't really need to know it. It's not true. Some of it is true, but not all of it. So anyway, the electrons are the planets, and they carry a negative electrical charge. So ready? It's negative, right? That's like, I don't think that actually works on that one. So negative, or okay, minus. I don't know. We'll have to figure out some little, you know, thing that you can do on that one. But they're basically the planets. They carry an electrical charge, and they're also what determines the chemical properties, right? Because they are what you give up, and what the and ions and atoms, they give those up, and they take them, and they share the electrons. So here's some more of those atoms. And if they were pure, if you know, solid, just pure atom, just a natural atom in its purest form, then it would have the same amount of protons and the same amount of electrons in every instance. But an atom that is just a pure atom like that does not exist in nature. They always ionize, and they ionize because they're giving up some of their electrons. And what we're worried about, or working with we're not worried about it. Oh, this is stressing me out so bad. There's only 12% on chemistry on this test, so don't worry about it, okay? But what we're focusing on in these classes are the electrons in the outer orbit. So in the case of nitrogen, for example, you have 1, 2, 3, 4, 5 electrons in its outer orbit. Okay, so nitrogen, if it's going to stick to something, would be looking for something with 3 electrons in its outer orbit that it could marry up with, because that would give it its inert status of 8 electrons shared. And so it's the outer orbit that we're mostly worried about. You'll see that some of these have other inner orbits, and those are important in chemistry, but not with what we're talking about, not the depth of stuff we're going to talk about. We're focusing on the outer orbits here. Okay? So oxygen, you'll see, has 6 electrons in its outer orbit. So it's looking for something to stick to that has 2 electrons in its outer orbit, or a couple different other atoms that have 2. For example, 2 hydrogens. A hydrogen has 1 electron in its outer orbit, so if you have 2 hydrogens, then that forms that 8 electrons that would make oxygen really happy, right? Sodium, looking for something that has 7 electrons in its outer orbit because it only has 1, and coincidentally, chlorine does have 7 electrons in its outer orbit, okay? So sodium chloride, that's why those two go together so nicely. Remember, the magic number is 8. Everything is happiest when it has 8 electrons in its outer shell. Closer to 8, the happier it is. So an ion is an electrically charged atom or a group of atoms. So water is extremely stable. Remember we talked about this? Okay, water is for some reason the Mickey Mouse ion. Okay, now I was having a conversation with Dr. Lubner, Tanya Lubner, down at National WQA this last year, and chemists think that this is way too oversimplified to call it the Mickey Mouse ion. I myself am not a chemist, nor did I go to school for chemistry, nor did I actually pass chemistry easily. It was maybe one of my worst subjects ever. It's so funny that I'm now doing this. So I had the conversation with Dr. Lubner that said, you know, this puts it simple. On the picture, the diagrams, the clip arts and everything, it all looks like Mickey Mouse to me. So, you know, looks like 2 ears and a face, and so, I mean, not a face necessarily, unless he's got like zits or something, like what the acne, Mickey with acne. There's a ride at Disney. So basically, just so you know, if you ever decide to get a PhD in chemistry or to further your degree in chemistry, this may not be exactly right, but a lot of the stuff that we talk about as we're learning it isn't there either, because these are not like straight circular orbits either. The electrons, they're like zigzagging all over the place and going all over the place. So we're just trying to keep it simple so that you understand the basic concepts here. Okay, but water is extremely stable, and what that means is that you've got 8 electrons, and it's you know, it's shared, right? So it does not like to release any of those ears. If you cut off one of Mickey's ears, it doesn't like to do that. It likes to have both of its ears. Okay, it likes that. Mickey likes to have 2 ears. And by the way, when it comes to water, water hardly ever gives up both of its ears. So oxygen hardly ever gives up both of its ears. So what you end up with is, if it does ionize, okay, which means that, remember when we took salt, this is what we called ionized, okay? If you take salt, sodium chloride, and you put it in a solution, then the sodium goes one direction. You guys should see me, I'm gesturing like crazy right now. It's kind of funny. So, like, I got to remember that you guys can't actually see my hands. So if you take salt and you put it in a solution, the sodium goes one direction, the chloride goes another direction. They've ionized because the sodium has a positive charge, the chloride has a negative charge. They've ionized. Well, water as a compound, it doesn't like to do that. It's extremely stable. It doesn't like to give up any of its ears, basically. Okay, when it does, so that makes water non-ionic, which means that it shouldn't ionize at all. Okay. However, water will ionize just slightly for a fraction of a second on occasion, and when it does, you have a positively charged hydrogen and a negatively charged hydroxide. They call it so. Mickey, basically, when water does ionize, the oxygen and one of the hydrogens stays together, And it still is a negatively charged ion because one of the ears took away the positive proton, but so that would make the hydroxide ion a negatively charged ion. It's just a little cartoon. I thought you said the chemical composition for water was H2O. Did it? Okay. So when water does ionize, like I said, you have the positively charged proton and then the negatively charged hydroxide. It forms a hydrogen ion with positive charge and a hydroxide ion with negative charge. I'm hit. I've lost an electron. Are you sure? I'm positive, right? Because when you lose an electron, it becomes positively charged. Okay, so ions again. Then this is just a little review from last week, but it's important. Okay, so the sodium atom has 11 protons and 11 electrons. It has 1 electron in its outer shell. The chlorine atom has 17 protons and 17 electrons. It has 7 electrons in its outer shell. So the sodium loses its 1 outer orbit electron. That means it still has 11 protons, which have a positive charge, but only 10 electrons, which have a negative charge. That gives the sodium ion a positive charge and makes it want to seek out ions with a negative charge. The chlorine, now a chloride ion, gains 1 outer orbit electron. That means it still has 17 protons, which have a positive charge, but now also has 18 electrons, which have a negative charge. That gives it a valence, a negative valence of 1, by the way. That's valence. Oh, we talked about that last week. This gives the chloride ion a negative charge and makes it want to seek out ions with a positive charge. Okay. Terms that you will need to know. Cation is a positively charged atom or group of atoms in solution. An anion is a negatively charged atom or group of atoms in a solution. Okay, so this is important because when we start talking next week about ion exchange, we're going to talk about cations and anions. Okay, a cation resin is a resin that removes cations. If a cation resin is going to remove cations, then it has to have a negative charge because a cation is a positively charged atom or group of atoms. That means that if something's going to remove or attract positive ions, then it has to have a negative charge. So a water softener that's removing positively charged calcium and iron has to have negatively charged resin in it. The terms oxidation and reduction, if you're looking at the official terms of those, a reduction means that the charge goes down. For example, a +2 would go down to 0, or a -2 would go down to -3. Oxidation is the opposite. Okay, so when you think about iron, for example, when you oxidize iron, ferrous iron is Fe++. Ferric iron or oxidized iron is Fe+++. So you've actually increased the valence. You've increased it. Okay. If you were to take ferric iron, Fe++, and reduce it, it would mean that you were taking the charge down. So a negative, you would take it down to Fe++, or Fe++. Okay. There's some common cations that we run across. Okay. Hydrogen, ferrous iron, aluminum, magnesium, calcium, ferric iron, sodium. Some common anions, negatively charged. We got hydroxide, which was Mickey with the severed ear. Chloride, bicarbonate, carbonate, sulfate, phosphate, nitrate. Okay, so acids, bases, and salts. When various cations and anions form in solution, they combine, and the resulting compounds are classified as acids, bases, and salts. Acids are compounds that release hydrogen ions in a solution. Okay, so we're going to talk about the pH scale a little bit more, just in review, but the compounds are a solution that have a lot of extra hydrogens in there. Okay, so they've got all these extra hydrogens. They're looking to give away their hydrogen. Acids have a characteristic sour taste, so think of lemon juice. They have the ability to change the color of litmus paper from blue to red. They react with bases to form salt and water. And they really like Pink Floyd music. Important to know. And that'll be on the test, I think, or probably not. Okay, bases are compounds that release hydroxide ions in solution and accept hydrogen ions. They tend to have a bitter taste. They have a soapy feeling when applied to the skin. They have the ability to restore the original blue color of litmus that has been turned red by acids. Okay, so litmus paper, if you get this question again, which you may, so litmus paper is normally blue, and if you want to turn it back to blue from red, then you're going to say, just remember the color, blue, base, right? So bases for high pH that's above 7, is going to turn litmus paper blue. So blue, base. It's just a one big Sesame Street episode. It's like, what is the valence of that iron? 1. 2. Anyway, that's a horrible impression of the count. They really wimped up the count. Remember when the count was scary? When there was lightning and everything? They made him so wimpy now, so they don't freak out and scare little kids. But I thought like Big Bird, a giant bird walking around with this gigantic. It was big enough to eat you. It was like a dinosaur bird. That was scary than the count. But, just my own issues. Welcome, everybody, to my head. Okay, salts. So when strong acids and strong bases get married, they form water and a neutral compound called salt. They're generally made up of metallic cations and non-metallic anions. And see, hey, look up here. See, this guy up here, there's a sodium, a little picture of the sodium, this soft, shiny metal, and then the chlorine's greenish gas. Sort of like being in a room with some people after they've eaten Taco Bell. That was just wrong, sorry. Anyway, all right, so acids yield an excess of hydrogen ions in aqueous solution. They have a sour taste, turn litmus paper red. They're characterized as strong and weak and monoprotic and polyprotic and blah, 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 blah. Who cares? No way are you ever going to be asked anything about a monoprotic or polyprotic or amphilite or non-amphilite acid. Bases yield an excess of hydroxide ions in an aqueous solution, which I think is funny. Aqueous is like, I don't know, it sounds so chemically unprofessional, but basically it's just a solution, like any kind of liquid. Bases have a bitter taste, and they turn litmus paper blue, and they'll also partially dissolve skin. It's always fun. All right, so hydrogen-containing compounds, some of them that you run into, water, carbonic acid makes water acidic and a stronger solvent. It often comes from the carbon dioxide dissolved in the water. We will be talking about carbonic acid more next week when we talk about water hardness and ion exchange. Because a lot of times carbonic acid is what forms with water up in the atmosphere and makes acid rain. Also, you have hydrochloric acid, sulfuric acid, phosphoric acid. Those are often chemicals used in water treatment. Well, actually, we're going to go and talk about it now. How about that? Let's talk about carbonic acid now. So calcium compounds, because we're going to talk about some of the stuff in the water. So let's go on and do that now, shall we? Okay. So calcium compounds, calcium hydroxide, calcium chloride, but the ones that are most relevant in water treatment that we run across most commonly are calcium bicarbonate and calcium carbonate. So what happens, right, is you've got all this carbon dioxide up in the atmosphere, and it forms with water to form carbonic acid, okay? When it hits the ground, it starts to dissolve this, because it's got this slightly low pH, it dissolves the calcium carbonate. So what we run across, what's in the ground, the calcium, magnesium that's in the ground, so the calcium there is calcium carbonate, CaCO3. Okay, it's in the ground until the rain dissolves it. When the rain dissolves it, it becomes calcium bicarbonate. Okay, so that's dissolved rock. So when we do our little water test, and we're dropping our droplets in there, and we're turning it from pink to blue, what we're testing for there is the temporary hardness, or the dissolved hardness, or calcium bicarbonate. That's calcium bicarbonate. So when the carbon dioxide leaves the water, and what you have left is the reformation of calcium carbonate. And so what we get built up around the faucets and the shower heads and in the pipes and the plumbing and all that, that's calcium carbonate. So that's rock that has turned back to its solid form, to its non-dissolved form. So when the water heats up, the carbon dioxide leaves the water and causes reformation of calcium carbonate, or scale. Same thing happens with magnesium. The hardness due to calcium magnesium bicarbonates in the water is referred to as temporary hardness. You will probably see that again. Calcium bicarbonate is temporary hardness. Calcium bicarbonate is temporary hardness. Okay? This is due to the fact that the bicarbonates will revert back to an insoluble form when the water is heated. Some sodium compounds that you run across. Sodium hydroxide, these are used as an acid neutralizer. Sodium chloride, used to regenerate water softeners. That's interesting. Heard of that stuff. Sodium bicarbonate contributes to alkalinity. Sodium carbonate, used as an acid neutralizer. Sodium sulfite absorbs oxygen. They're used as a reducing agent. Sodium sulfate, the byproduct of water treatment. Probably not going to need to know all of these things for the exam. It's just information. Okay, alkalinity. Alkalinity, you know, this is a big issue, and it's become bigger and bigger and bigger across the country. People have, you know, you've got the Kanger machines, or the Kangen or Kanger, and you know, these things. A lot of the reverse osmosis people are putting alkalinity filters on, and there's just this big hoodoo right now about, oh, you shouldn't drink reverse osmosis water because it strips all the good minerals from your body and it lowers the pH so much, blah, 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 blah. It's all a bunch of, oh, well, it's just fun. Anyway, we will talk about sometime, there's some pretty excellent resources that WQA has information-wise on the, for alkalinity and how to address the alkalinity filters and stuff like that. And let me just give you guys a little hint here on how I address it. Okay? Because a lot of people are running into the alkalinity filters, and those of you that want to know this stuff, this is exactly the kind of stuff we talk about, by the way, on Thursday morning's MB Pro calls. So we can, if you want to know how to address these things or how to deal with them, or want to know questions or any of that stuff, we talk about on Thursday mornings. We have an MB Pro call, free. Log on. You can find it on my website on the upcoming seminars. We have sales professionals, and not only sales, but people from all over the country on this call, and we talk about questions like this. So alkalinity, alkalinity itself is actually caused, I mean, just in terms of what we're talking about in terms of chemistry here, it's caused by the presence of bicarbonates and carbonates and hydroxides in the water. But you know how you run across those people at the health and fitness shows or your customers or whatever, and they're so proud because they just spent $2 on some machine that adds alkalinity to the water so that they never ever get cancer. Here's my take or how I address that stuff. Okay. First off, I'm not even going to argue about whether or not the alkalinity helps or doesn't help. Okay. I have an opinion on it. I've read it. I've researched. I know what my opinion is. But I'm not going to get into an argument with somebody who obviously knows more than I do because they read their Amway brochure. So what I'm going to do is I'm going to say, sure, maybe it does help. There's two issues there. Number one, I can put an alkalinity filter on this reverse osmosis system for way, way less money than that little counter thing that you're going to put on there. And secondly, let's say that it does help, that the alkalinity is good, that it prevents you and your family and everybody else who shops at Walmart regularly from getting cancer. Not that everybody that shops at Walmart is going to get cancer, nor is everybody who shops at Walmart bad people. So I just should clarify that the opinions expressed herein are not those of the Water Quality Association or Moti-Vitality. Anyway, they're solely mine, Kelly Thompson, and I'm feeling kind of warped today. I really needed more coffee, I think. So anyway, what I always tell people when I do run across this stuff is, so maybe it does help. If you want to believe that, that's great. And what I would suggest to you, though, is that it's great to start off with a starting point. So you're adding alkalinity to water that has a bunch of other stuff in it. Why not start with exactly what you know is there? I mean, this is why flower shops a lot of times will use reverse osmosis or distilled water for their plants. They'll take out all the crap in the water that's not good for the plants, and they'll start with a high quality, high pure water, and then they re-add back that plant the vitamins and the minerals and the nutrients that plant needs to grow and flourish. So that's kind of the same philosophy I have when it comes to my drinking water. I'm going to take all the stuff out of the water first, as much as I can, start with a high-quality, purified water, and then I can re-add back whatever I want, whether I want to put alkalinity back into it or whether I want to add vanilla flavoring or lemon flavoring or whatever I want to put in it. I can add that stuff back in, but I know what I'm starting with. I have a starting point. That's kind of how I address the alkalinity thing. Is like, yeah, they're not competitors. One's going to help the other. If you want to put your alkalinity stuff in there, that's fine. Put it in there. But at least you have a base. You know where you're starting from when you're starting with reverse osmosis water. You're not adding alkalinity to all the other crap that might be in the water first. Anyway. So alkalinity itself is caused by the presence of bicarbonates, carbonates, and hydroxides in the water. That is just my opinion, and I hope I didn't offend anybody that is really into the alkalinity stuff out there. That is strictly an opinion based on the research that I've done or what I've run across. But I don't think they're competitors. I don't think that the alkalinity filters and the ROs have to be competitors with each other. I do get a little annoyed by people who really don't know what they're talking about and think that they do because they read a brochure on it or went to a rah-rah get-rich-quick seminar. Alkalinity does have a drying effect on the skin, and it tends to have a soda taste. Sorry, you guys got to listen to my alkalinity rant there for a minute. Hope everybody's still there. You guys awake? I don't think any of that will be on the exam. Carbon dioxide is usually more in surface waters. Does bacteria like RO water or alkaline water? Bacteria likes water that is neutral as possible, so the two are going to be different. I mean, you can actually have RO water that has a high pH. And that's the thing. Okay, just so you know, reverse osmosis will take out or will lower the pH of the water a little bit. But if your pH was 8.5 before the reverse osmosis system, when you ran it in, if you had a high pH of 8.5 when you ran it in, you're still going to have basic water, and that RO water is still going to have a high pH. The reverse osmosis is only going to take it down about half a spot. So if you started at 7, the RO is going to take the water down to 6.5. But it's not because it's lowering the pH. What it's doing is it's taking away things that are binding to the hydrogen. Remember, hydrogen is teeny tiny. It's itty bitty. Okay, so what you're doing is you're taking away things that would bind that hydrogen up. So because remember, the definition of an acid is an aqueous solution that has extra hydrogens to release. So you're taking away the bigger things. Reverse osmosis is taking away some of the bigger things that would bind up that hydrogen, that would collect that hydrogen, that would stick to that hydrogen. Hydrogen's teeny tiny, it's itty bitty. So that's why the pH gets lowered, because you do still have some of those leftover hydrogens in that RO water. Okay. So if you have a high pH running through that reverse osmosis system, water that has a high pH, you're still going to have a higher pH. It's still going to be basic. You're not going to always, just because you run water through a reverse osmosis system does not mean that it makes it acidic. So bacteria likes neutral water. I will tell you that. Bacteria likes water as close to neutral as possible. And so that was a Cameron. Oh, okay, that was a private message. Brenda, sorry, I'm reading a private message. Brenda, it was. I don't think so, Brenda. You're not too much over your head. Okay, so carbon dioxide is usually more in surface waters. It combines with water to form carbonic acid, and it's usually associated with low pH. Fluoride is almost always present in natural water supplies. It can cause a bad taste in the water, and it can have a corrosive effect. It can cause problems with softening as well, because if you have a lot of chloride in the water, then you're competing, right? If you have a lot of those chlorides, then you're actually, the calcium, if you have a water softener that has a negatively charged resin in there, if you have a lot of chlorides in the water, calcium is going to have to make a decision of whether or not it wants to stay stuck to the negatively charged chloride in the water, or whether or not it wants to stick to the negatively charged resin. So if you've got that resin, a lot of chlorides in the water, then it can make softening the water a lot more difficult. Fluoride, here's another one of those lovely controversial topics, and I'll say the same thing. Okay, first off, you ever want to know about fluoride? I mean, fluoride is naturally occurring. One of the things, it was not a government conspiracy placed in the water to give everybody cancer and to make us all watch old reruns of Bonanza. I don't know. It sounds as ridiculous as anything else. But fluoride's naturally occurring. It's out there. Here's what I do know. Fluoride will cause, brittling of bones and brown stains and stuff like that on your teeth at levels over 4 parts per million, or actually it's per billion, I think. No, it is per million. Okay, so it can be beneficial at low levels, 1 part per million, but detrimental at high levels above 2 parts. Okay, and so you Google search fluoride, and you're going to find all this controversy over whether or not fluoride should be ingested. Some people say that it's good for your bones. Some people say that it's not good for your bones. I know that at high levels, it's not good for your bones. my philosophy on it is the same with the alkalinity. Start with the base, okay? If you want fluoride, I mean, the toothpaste tube says don't ingest it. I mean, I don't want to, I like my well water. I like having a reverse osmosis and knowing what I'm starting with, but even if I were on city water, I would take it all out, take everything out, and then I would re-add specifically back to the water what I need. You know, so use the little Axe mouthwash and stuff like that. But that's coming from a 42-year-old man who's never had a cavity in his life. And yes, I am bragging about that. I have never, ever, ever had a cavity in my life. So, and I drink reverse osmosis water, have for years. So there. Yeah. So hydrogen sulfide. There's a lot of research. If you Google search stuff, there's so much information on fluoride out there that you can find it and then make your own opinion. Ask your dentist. I mean, I bet you there are very few of you listening to this call right now that are actually dentists. Okay, so hydrogen sulfide in high concentrations, it's flammable and poisonous. It's corrosive to metals and it tarnishes silver. And you know what, there are places like, we have clients down in Ohio, for example, that have massive amounts of hydrogen sulfide. And wow, I can't imagine, I don't even know how people live like this. Holy moly, you can smell it. Just driving through the town, you can smell it, but they can't keep in their house because of the gas. They can't keep electronics. I mean, all the electronics will corrode and destroy and tarnishes silver. It'd make your eyes hurt. It's bad. It can have a laxative effect too, and it really stinks, like really stinks. Iron, we can talk a lot more about iron later, but iron is usually less than 5 parts per million. It can be as high as 60 parts per million. It gives a metallic taste to the water, and it stains at levels as low as 0.3 parts per million, 0.3 parts per million. And like I said, we are going to talk a lot more about iron next week and actually in a couple of weeks when we talk about the troublesome trio too, more about hydrogen sulfide and manganese too. But ferric iron, ferric iron is iron that's already rust, or you can see it. It's converted to, it's oxidized. The way I always remember the differences in these is ferric ends in a C, so you can see it. And ferrous iron is clear water iron. A water softener, by the way, will not remove ferric iron without some other form of filtration. You need other forms of filtration on that. A ferrous iron is clear water iron, and a water softener will remove ferrous iron. Manganese comes in the same forms as iron. It usually accompanies iron. It's not oxidized easily, so ion exchange is the best treatment method. And it will cause dark brown or black stains at levels as low as 0.05 parts per million. That's different. So 0.05 for manganese, 0.05. Nitrate and nitrite. And here, I look for, every time I give this course, I look forward to this because this is just one of the most fun slides I have. So nitrites and nitrates do occasionally occur in nature, but they're usually an indicator of organic matter or pesticides and fertilizers. And here's the thing. They're usually found in shallow wells. And, okay, ready? Everybody say it with me. It causes a disease called methemoglobinemia, or blue baby syndrome. Methemoglobinemia. And what that is, what methemoglobinemia is, and the reason I like that word so much is it's so much fun to say. You guys should try it. Just try and say methemoglobinemia. And if you're successful with that, try it like 10 times in a row. And my thought is that if you walked into a smoothie shop and you just said to the owner, hey, if I could say methemoglobinemia 10 times in a row without messing up, can I have a free smoothie? I bet you that they would be so impressed if they gave you your smoothie of any flavor and your choice. So far, nobody has ever, ever taken me up on that. I don't think that, to try it, but I would love to hear somebody report back to me and tell me how that went. So methemoglobinemia, or blue baby syndrome, what that is nitrates prevent the red blood cells from carrying oxygen to the extremities. So mostly people with weak hearts, like babies or elderly. So the reason they call it blue baby syndrome and this has been attributed to a lot of the sudden infant death syndrome, SID. And I don't think that part is funny at all, just so you guys know. That's not funny. The exact opposite of funny, in fact. But what it does is it prevents, so the red blood cells can't carry oxygen, and that's why it gives the skin, blue, it makes it blue. They don't have oxygen. So Jim's saying that you might want to know about nitrates and nitrites. They're an indicator of organic matter, fertilizers. I'm speaking as well as Jim's typing. Okay. All right, silica is not a problem for most residential treatments. I don't know why you get the little top thing up there. Makes no sense though. It's a problem for some arsenic removal systems. It's a big problem for the industrial field because of extremely hard scale into boilers and on turbine blades as an after effect of steam. Sodium is found at some level in most water supplies. It increases the corrosive action if there's a lot of it. The only way to treat it is through deionization, distillation, or reverse osmosis. Methane can be a fire and explosion hazard, and in fact, we are seeing more and more methane in the water. I mean, it does occur naturally in the water, especially when around marshlands where you have, or dumps, actually, which wouldn't be natural, it would be put in there, but you're seeing a lot more methane in the water recently because of the hydraulic fracturing, the fracking issue. Do a YouTube search sometime on flammable water. It's pretty wild. You'll see some pretty amazing stuff there. It's been a big issue on the East Coast because of fracking. And not only the East Coast, here in Michigan we have some. EPA says it's fine to drink, you just don't smoke in the toilet. It will explode. We will talk more about methane and how to treat it in coming weeks with open aeration systems. Okay, the pH scale. The thing with the pH scale is pH. You know how when you grow up and you always learn AD stands for after death. That's what I always learned growing up. Is that AD stands for after death, right, on the scale. That's actually not what it means. It's actually a Latin term called Anno Domini, which is Latin for Year of Our Lord. So AD stands for Year of Our Lord, or Anno Domini. But pH, it's kind of the same thing, because with pH, even in the book, it says potential of hydrogen. So when you go to the book and you read, or when you're talking to somebody and you're saying, what does pH mean? Well, pretty much everybody out there agrees that pH means potential of hydrogen. If you Google search it, then it's even going to come up, potential of hydrogen. That's not what it means. Yeah, that's actually not what the P is always a lowercase p. The H is a capital H, and that stands for hydrogen. So the P, the lowercase p, is a mathematical shorthand for the negative log base 10 of a number. H is the concentration of hydrogen ions in moles per liter, which is a measurement. Okay, so the only way that becomes relevant, because see, the thing is, if you Google search what does pH mean, and it's going to come up, and 95% of the results are going to show potential of hydrogen. But if you happen to be talking to somebody that has a chemistry background or actually knows this stuff, then I think it would be helpful and handy to understand that P doesn't actually, that the pH doesn't actually stand for potential of hydrogen. It's actually a mathematical symbol. But basically, the potential of hydrogen does say what it is, because remember, a low pH means that it has a lot of extra hydrogens to release. Okay, and so the pH scale, obviously 7 is neutral. That means that you have the exact amount of hydrogens as you do hydroxides in there. And the higher the scale, the higher the scale down here. The higher the scale, the more hydroxides you have to release. The lower the scale, the more hydrogens you have to release. pH is measured in the field to determine if water has the potential to be corrosive, so it's a field measurement, or have a bitter taste. If it's low pH, it's going to be corrosive metals. If it has a high pH, it's going to have a bitter taste, or whether or not it has the possibility to form scale. So it's a field. pH is a field measurement. The pH scale goes from 0 to 14, 7 being neutral. pH 7 means you have an equal concentration of free hydrogen ions to substances that want to bind them. Substances that want to bind hydrogen ions are called bases. The pH scale is a tool for judging what to do with the water in the field. If the pH is below 7, we know we have excess free hydrogen. We need to add something that wants them, like carbonate or calcium carbonate or lime. If you have pH above 7, you have more alkaline substances than free hydrogen ions and need to add something like citric acid to bring the pH down. The pH scale is a logarithmic scale. What that means is that a pH of 8 is going to be 10 times more basic than a pH of 7. So basically you just add a 0 every time you go up through, okay? So a pH of 12 is going to be 100 times more basic than a pH of 10. A pH of 3 is going to be 1,000 times more acidic than a pH of 6. Okay, so you add a 0 each time. It's logarithmic. I like this scale actually. This is pretty. This image because it just shows some of the common stuff that we run across. Stomach lining. Look at this. Hydrochloric acid secreted from the stomach lining. pH of 1. It's 1 million times more acidic than a pH of 7. That's pretty wild, isn't it? All right. So just some review questions here. Iron, present in water in excess of as little, make sure everybody's muted here, getting some background noise. We got a couple minutes here. We have a couple minutes. So do you guys want to do what you did last week? We'll go through these and you guys can just toss out the answer. We're going to go through it a little quicker, but if you want to chat the answers here, that'd be great, just to kind of quiz yourself. These came straight out of the back of the Water Treatment Fundamentals book. So iron present in water in excess of little as blank can cause staining of plumbing fixtures. Point 3, good. Water is an extremely blank compound. I'll make you guys, I won't make you guess the numbers here, but it's an extremely stable compound, and it contains 88.812% of oxygen and 11.188% of hydrogen. Protons and neutrons of an atom are to be found in the blank. What do you guys think? Nucleus. Very good. Very good. Atoms that are related, that is, have the same atomic number, but have different atomic weights, are called, these are isotopes. We didn't talk a lot about those, but the book does. The union of two atoms, one of hydrogen and one of oxygen, has the formula OH negative. It performs as though it were a single atom, and it is called, so this is Mickey with a severed ear. What is that? You guys remember? Mickey with a severed ear. What is the OH negative called? It is a hydroxide ion. Hydroxide. Fluorides can be detrimental or beneficial to water. They may cause a dark brown stain to form on teeth. True or false? True or false? That's true. Good. Chlorides seldom are found in natural water supplies. True or false? That's false. You guys out. pH indicates the degree of intensity of the acidity or alkalinity of water. It's true. Good. Sodium can be removed from water only through such processes as distillation, deionization, or reverse osmosis. True or false? That's true. Good. They're moving now. Manganese oxidizes much faster than iron. For this reason, it's generally easier to remove from water. True or false? False. Good. Yeah, it does not oxidize as easily. Alkalinity is caused by the presence of bicarbonates, carbonates, and hydroxides in the water. It's true. Salts are substances containing metallic cations and metallic anions. Interesting. This one is false. Good. And this is an example of the kind of crap questions they sometimes put on this exam too. Just I mean, you look at it and you know. So salts are substances that contain metallic cations and non-metallic anions is what would make that true. And so you read it. When you read the questions on this exam, you got to read them carefully. Go slow. Read them carefully. Make sure you know what they're saying. A pH of 2 is 100 times as acidic as a pH of 4. True or false? pH of 2 is 100 times as acidic. That's true. Good. Surface waters generally contain more carbon dioxide than well waters. True or false? That is true. A pH of blank indicates a neutral water with acidity and alkalinity in balance. You guys should know this one. 7. Good. Oh, it's yeah, 7. It's a multiple choice. Okay, magnesium sulfate found in water is highly soluble. You guys, you're not going to even know that. It's extremely soluble. It's magnesium sulfate. Yeah. All right. That's it for today. Next week, just a reminder, because a lot of you are taking the test at EWQA and want to make sure that we finish on time. Next week, we are going to do week 5 and 6. That's going to make class about 2 hours long, okay? So we're going to do week 5 and 6 combined. So give yourself a little bit extra time next week. And then just so you know, you're looking at water clinics, and you want to know about water clinics and home shows. In 2 weeks, we have a webinar. It's free for MD members, which most of you on this call are. Please let us know if you want to register. We have spaces limited, but we're going to have a discussion about how to do water clinics and home shows and really generate some leads and stuff like that. So let us know there. And as always, please join us Thursday mornings, 8:30. For MD Pro Call. We'd love to have you. And other than that, everybody have a great week, and I will see you or talk to you next week. Have a great weekend. And week. It's only Wednesday.